Last session we were able to utilize the keyboard to make our sprites move around on screen. And when the sprites are moving, we will talk a little bit about this concept of controlling their animation so they are walking. But then what we want to really concern ourselves with today is what happens when those elements intersect each other. Currently, you'll see when the bounding box for my unicorn and the bounding box for the blue eyeball intersect, the background turns yellow. There's some other code in there that will make the lives change and other stuff happen, and we'll walk through that in a little bit. But the first thing to think about that's happening is we are trying to figure out how and when they are intersecting. Now in this, each one of the elements, so I'm going to first just go into the enemy quick here and modify it. So I'm just going to put a rectangle. And position this rectangle where the artwork is being displayed. But I need to put it down here. And we'll talk through some of these other lines of code that were given to you with no explanation so that we can better understand what is going on here. Oh wait, we do position first, so we'll draw it. Draw this rectangle and then draw it at. So if we look at it, you can see that there's now a green box that corresponds to the bounding box of that unicorn. And if intersection occurs even at that top corner, you'll see that it counts even though the unicorn technically has not run into the player yet. Same thing with the back corner. So what we are looking at is true box-on-box collision. We're not doing pixel-based collision where we're comparing the colors in one pixel to the colors in a different pixel to see are they different, therefore has an intersection occurred. But instead what we are looking at is the general bounding box or rectangle that makes up my image, and does it intersect the other element. Looking into the Sprite class, so this is the Sprite class, which is at the end of the file. And inside the Sprite class, it is drawing itself at x minus the width of the object divided by 2 and the y minus the height of the object divided by 2. So what it's effectively doing is drawing the artwork so that the artwork is centered on the x and y coordinate. And the reason that we do it this way is when we start doing more advanced movement so that we are moving on an angle instead of only moving in a horizontal or only moving in a vertical direction, it's important that we are now moving around the center of the object instead of moving or measuring from the top left corner of an object. Otherwise, rotation values get really weird when something rotates around its corner instead of rotating around its middle. And that will become more apparent. So it made sense because we could just draw this at x and y, draw the other one at x and y, and be done with it. But it makes more sense to start doing this because it will prep us for more advanced movement styles, but also for being lazy, and I emphasize that, being lazy with the enemy. Because the enemy is able to draw itself You can just indent these so we can better see what's going on. By flipping itself over. So if, as you look through the code, the enemy or the unicorn, when it draws on screen, it is flipping it's flipping along the y-axis, but that means it's essentially doing a horizontal flip. So if the y-axis is vertical, it is now flipping horizontally. And that's how the unicorn switches from pointing left or pointing right. And it does it by doing a scale of -1 or 1. 1 is the natural state of an object. -1 means we are going to scale it horizontally all the way around. If we think we're kind of squishing the graphic, then eventually the graphic flips itself. So that's what scaling to -1 does. That causes the horizontal flip. There is no flip horizontal command built into the language, because a flip horizontal is just scale of -1 on the x-axis. That's how it is put together. Now this translate x and y and push matrix and pop matrix, we'll get into those a little bit later. For now, you can just pretend you didn't see them, and it's all good. But you will notice when I say translate x and y, when we're drawing the image here for the unicorn, it doesn't say x minus w divided by 2 and y minus h divided by 2. It just is negative w divided by 2 and negative h divided by 2. Because what is happening is we have temporarily changed our 0, 0 coordinate from the top left corner of the screen and moved it to wherever x and y are, and then we're able to draw our artwork at that point. So when we start using it, and then if you try to do something without using it, you'll quickly go, oh, that's why I need to do that, and then it will make a whole lot more sense as we move forward with it. But we will be talking more about matrix and translate and how that works. But the scale is how we are flipping the player. So our objects are being drawn around their center point, and that's an important thing to keep in mind, because as we look at intersect, what happens with a rectangle intersect, it's just like doing the circle intersect, where we had the radius of each object and we compare the distance apart of object 1 versus object 2 and decide, is that distance greater or less than the sum of, when we did circles, it was the sum of the two radiuses or radii. But with rectangles, we are using half width and half height. With it being a circle, we have the advantage of the height and the width are the same, so all we have to do is one check. But with a rectangle, because a rectangle can be long and skinny, or short and fat, or a rectangle could be square, so it would have the same values. But we don't know that, so we assume on a rectangle that the height and width will not be equal values. So we have to do a check where we first check the distance on the x-axis, and is the distance apart on the x-axis less than the combined half widths? And if that's true, then we will check if the distance on the y-axis is less than the combined half heights, and if that's the case, we return true. But if that's not the case, then none of that will happen, and we will just return false, meaning our two rectangles are not intersecting. So our first step is we create distance x, which is the distance apart. Then we say the distance y, the distance apart on the y-axis. Then we figure out half width, figure out a half height value. And once we have those four numbers, we're able to then do this nested if statement to find out, are the two objects intersecting or not? So the rectangle intersect, it's just like in the catcher game with the drop circle based collision, except we're now checking on both the horizontal and vertical component. It's the same thing as, are they intersecting or not? So when we ask that question, we say, hey, if the rectangles have intersected, well then, in this case, I made the background turn yellow and with these two lines. But we also have, we can remove a live function in here and see how that goes in a little bit. So once again, looking at the sprite, when it is walking, as it's walking, it displays itself at x minus half of its width and y minus half of its width. If we drew the image at x and y, it would be drawing from its top left corner. And then our intersect function would be different. And when we move to being able to rotate objects, it would get really out of hand and we'd have to redo a bunch of things. So this is why with the unicorn, we're cheating. We're using translate. I'm using translate x and y. If I draw a rectangle at 0, 0, 200 wide, 100 tall, we can see it draws, again, from the top left corner. That's where things want to draw. But if I say translate, and this time I say translate to 300, 300, I've effectively moved that 0 point. So now when I run my sketch, we'll see that now I went over 300, down 300, and now I drew my rectangle at 0, 0. So translate takes what was in this top left corner, 0, 0, and moves it to whatever point you want it to be. Now it stays there until it receives some other command. So if I were to say something like rect 100, 100. So this would be a smaller one. And we'll now see that it went 100 from that new 0. It didn't draw it up at 100, 100 up here. It's drawing it based on that 0. If I enter in a command and say push matrix, what that does is that says, remember how the world was before you heard the command push matrix. And then I'm going to translate. I'm just going to indent these just so it's easier to see. And then I will say pop matrix. So I'm going to remember the world, do a translation, draw, say pop, and now the world's back to how it was before I did my translation. And when I run my sketch, you'll see that the second one indeed draws at 100 by 100. So when we do a matrix transformation, what happens is the transformation that we do where we translate and rotate and do other cool stuff like that only affects what's inside that push and pop matrix section, but it's not going to then affect it later on. And the reason that this really starts to matter is if I were to say something along with my push and pop matrix, if we start playing with rotate, and let's say pi divided by 2. So it's 2 pi around a circle, so 4 pi will be or half a pi is going to be 90 degrees. So effectively I'm doing 90 degrees. Now let's see, rotate. Oh, let's not do... Okay, that puts it at a 45. So we can see how the one rotated, the other one didn't. Now, if we get rid of these lines, let's see, they're both rotating. If I get rid of the translation, you notice it's rotating around this 0, 0 point. So that's not really a useful way of rotating. So it's rotating around the 0. Now if I put back in the translate, so at least it's on screen, we can see it rotated from that corner. And if we translate instead to different amounts, then we can control that rotation even a little bit differently. Now, if I were to have another rotate command in, so we can rotate our objects. So the first object rotated from this point, and then the second object is rotating from that point as well. So we can see how it's moving based on, you could almost draw a circle through that corner right there, and that's how it's starting to rotate itself around. So it's not a really useful way of working with that, but if instead, when I go to rotate things, if I start using the matrices, I'm able to contain things. Now we'll see how they're behaving a little bit different. So the general rule of thumb is every object you draw, when you start using flips and start using rotations and things like that, every object is going to have its own push and pop matrix command. So you push and then you translate, you rotate, you do other stuff, and then when you're done with that, then you pop out that matrix so that the next object doesn't get affected by any changes that I did here. And that will give us a better way of working with it. At my draw function, I'll see the sprite draws itself. We check for intersect, or the sprite and enemy update themselves. We check for intersect, then we display, and then I draw the text. Well, if I use translate so I can get my object to flip properly, but don't use a matrix to control that translating, then we run into problems. If I don't have the translate going on, if we put X and Y back here, so if you notice, it flips, but it's going to be flipping along this line here. So every time it flips, it's gone. It's no longer there. So this is part of why we have to use the matrix as part of our keeping track of our transformations. We translate to that location, work with it. Didn't talk about walking in any great depth last time. Just going to point out a few things about walking. Is the easy fix for making something walk is if it's moving In this case, when the player is, oh, that's an enemy. Let's look at the player. It's even cleaner code to look at. If the player is going to be moving, walking is true. But if the player is not moving, so if you're not pressing one of the keys down, if you're not pressing up, down, left, or right, walking's false. Because if you're not pressing one of those keys, then there's no way you're moving, therefore walking is false. So that's the easy way. Instead of on all the negative ones putting it in multiple times, just to have one statement. If you're not pressing up and down and left and right, so if you're not pressing anything, then walking's false. Because the only other possibility is you were pressing one of those keys. So that makes it easy to take care of walking. And when walking is true, current frame goes up by 1. Otherwise, we reset current frame back to frame 0. And then if current frame has reached the total number of frames, then we make it go back down to 0 as well. That's the easy way to make the character walk. The one important thing is, before the character was walking, when you didn't care about walking, you have the line in there of current frame plus plus. You have to make sure you ditch that when you implement walking code. Otherwise, you will have current frame going up 2 every time, and then that will cause you to hit out of index array number issue problem. And we don't want to go there. So last session we left it where we just said current frame go up if the current frame is equal to the number of frames. When we do that, we see the character is moving the whole time. But if we want the character to only animate when we are actively engaged in movement, comment that one out, bring back these lines, then that allows the character to animate when we press a key. So we can see how it is indeed working. The enemy is about the same, except the enemy decides if it's chasing the player, it must be walking, otherwise it's not walking, because it's not tied to left, right, up, or down, or any of the keys. So we need some other way to keep track of it, and it's either it's chasing the player or not chasing the player. And when it's not, walking's false. Speeds are 0. Otherwise, walking is true, and then we figure out how to make it move towards the player. So with that, we have walking capabilities. We have intersection going on using half widths and half height. Other item is to figure out this removing lives, because if we're not intersecting, it's really just not that much fun. So if we intersect, I just wrote a quick function called remove life. Remove life takes our number of lives, takes it down by 1, and it resets the positions of the objects. Because if we don't do that, we will see, if we just take lives away when we intersect, we'll see that very quickly we run into a problem. That lives are just hitting the entire time we're touching, lives are going down. What we can do to prevent the infinite life option is to set it up so that when an intersection occurs, it takes a life away, and then it puts the objects in a position where they can't be touching each other. Now, this is one solution. There's other solutions you could devise. It could be if you intersect, that enemy goes away, or you go away and you go back to a starting place. You could institute a timer which temporarily renders you invulnerable so that you can get away. So after one hit, it now makes you, maybe you change color, you blink for a little bit. If you think like the classic game of Pac-Man, that you're able to, when you're invulnerable, after you eat the big dots, you're able to chase down the ghosts. They change in their status and you can chase them down. Other games, classic arcade games, you have like 2 seconds or 3 seconds of being invulnerable where you can at least move away from that enemy so you don't keep dying and losing lives immediately. So you could institute a timer, a shield type option, or in this case, the easy option is just they reset onto the sides of the screen so that they're no longer touching. If we made them show up in random places on screen, the problem could be at that point they appear on top of each other. So we would have to write the code to make sure that they show up in a random place but not touching. And you could do that. You could write more complex code than a simple 2-number random statement. Or you can just separate them like squabbling siblings.